Okay, in this video, I'm going to talk a little bit about structural equation modeling and the issue of model identification. The examples that I'm going to give are derived in part from a presentation in Schumacher and Lomax's Chapter 5 on path analysis from their Beginner's Guide to Structural Equation Modeling. So I'm going to use summary data that's presented in there along with variations on their example. Also, I'm going to be using the AMOS program to supplement the discussion. It is important to note that the issue of model identification can be fairly complex, but I'm going to be focusing on two issues that you need to pay particular attention to when creating and testing your structural equation models. So for starters, model identification speaks to the question of whether or not it is possible to derive unique estimates for a set of model parameters. Two key factors that can determine whether or not a model is identified are as follows. First, every latent variable, which would include error terms or disturbance terms, within a model must have an assigned scale. And then secondly, the model degrees of freedom must be equal to or greater than 0. So within the context of path analysis, the only latent variables or unmeasured variables are the error terms. So you'll notice in this path diagram right here that we have circles with E1, E2, and E3. And these are basically referring to prediction errors. Another term that's oftentimes used is disturbance. So basically it's just reflecting that portion of the variation in endogenous variables that's not accounted for by the variables that are predicting them. Also note that within SEM, there's a designation of endogenous and exogenous variables. So endogenous variables are those like this one, and this one that have arrows pointing to them from another variable within the model. Exogenous variables, which you can see right here, are variables that do not have arrows pointing to them. You do see over here that there's a double-headed arrow between age and years, but that's just reflecting covariation between two exogenous variables. So, basically, again, each error term represents the variation in an endogenous variable that's not accounted for by its predictor. So as noted previously, all latent variables, which would include the error terms or disturbances, must have a scale of measurement. And we can accomplish this by fixing the path coefficient from each latent error term to its respective endogenous variable to 1. So you'll notice in this diagram right here that we have a path that's for each of these that are fixed to 1. So we're scaling the error terms in reference to the endogenous variable associated with it. Now, to do this in AMOS, there's a couple of ways. The easiest way is to click on this little icon over here where it says add a unique variable to an existing variable, and that makes it really easy to draw out. Another option is just to literally draw out the circles and the arrows, but then you've got to manually fix those paths to 1. So kind of showing you what I'm talking about using diagramming here. Let's say that I want to call up my example data. And, basically, I'll just kind of draw it out for us. So we have, I'm just going to go ahead and draw out the basic model right here. So there's 1, 2, 3, I think there was another fourth one there, and then one down here. So in terms of the variables, we had essentially, if I can kind of go back to the model and look at it, we had sentiment as basically going down right here. We had age, and we had years right here. And in terms of the drawing, we also had deference leading to support, so deference leading to support. And we had years predicting sentiment, we had support predicting sentiment, we had age predicting deference, and support we had an arrow pointing in this direction. And we also had the covariance between age and years. So if I want my error terms included in the model, the easiest way to do this is to click on this button right here. So I'm clicking on it, and then I can click right here, right here I can move it around as well, and the same goes right here. So, and then essentially if I just right click on this, click on object properties, then I can name these. So I'll just name it E1, E2, and E3. And notice that by default the path coefficients are drawn. If I didn't use this particular option, I could still draw these out, but it's a little bit more of a pain in the neck because I would have to click on this little button right here to draw out the observed variables, and then use this button right here to draw in my paths, and then I would actually have to fix those path coefficients to 1. So I don't really want to do that. So here's a basic model, and so in this particular case, all of our error terms are scaled in reference to the endogenous variables within the model. So if I run the basic analysis, I can just ask for a few things that I normally might ask for, and then I'll click on this, and we'll just call this demo, and I'll just save over an older version. So now I've run the model, and you can see that I get under model fit statistics, you can see all those. There are my estimates. There's no problems with the model, and so forth. So that's just basically one issue that you have to pay attention to when you are running your models. So just keep in mind, all endogenous variables have to have an error term associated with them, and you have to scale those error terms in reference to the endogenous variables, and that means fixing those path coefficients to 1. So next up, what I will do is, oh, and by the way, this is just kind of an example right here where I drew these out with the error terms in AMOS, and this is just another example where I didn't fix the path coefficients to 1, and so when I ran the model, basically the estimates didn't come out. You can also see right here it says the model is probably unidentified right here, which is telling us that there's a problem. And then you can see that the model estimates are not generated, and you look at the regression weights, you can see unidentified, repeating. So there you go. So that's what happens if you don't fix those path coefficients to 1. Now the other issue is described by Klein as the counting rule, and this rule basically states that the number of parameters that are freely estimated in your model cannot exceed the number of observations in your covariance matrix. So the number of observations also is not referring to the sample size, but rather the number of unique or distinct elements that's contained within your variance-covariance matrix. And the number of distinct elements within the matrix is computed as p times p plus 1 divided by 2. So p being the number of variables. So here's an example of sort of a variance-covariance matrix. We don't actually have individual values in here, but these are just kind of reflecting the variances for a variable 1, a variable 2, and a variable 3. So along the principal diagonal right here, these are all the variances of the individual variables, and those are all unique within the variance-covariance matrix. When you look on the off diagonal, or off the principal diagonal, you have this little triangle here, and you have this triangle right here. The elements within these two triangles are, there's redundancy. Basically, the covariance between variables 1 and 2 is equal to the covariance between variables 2 and 1. So these elements right here would contain the same values. When we look at the covariance between variables 1 and 3 and 3 and 1, those values are the same, and the same would go between the covariance between variables 2 and 3 and 3 and 2. So what that means then, in terms of counting up the number of distinct elements, you can see that, again, the variances are all distinct, but we don't want to double count then the covariances. So either those in the upper triangle or the lower triangle will suffice. So we can count up these. That's 1, 2, 3 distinct elements there. So that gives us 6 distinct elements within the variance-covariance matrix. But if we want to just simply apply this rule right here, we have 3 variables, and then we're just multiplying that times 4, because it's 3 plus 1, which gets us 12. Divide that by 2, and that's what gets us the 6 right here. Okay, so In the context of regression and path analysis, then, the number of parameters being freely estimated in your model is going to be equal to the sum of the number of error terms within your model. So basically these error terms that we've designated here, and then the number of paths leading to all endogenous variables. So right here in this regression model, we've got the error, so there's a variance of that. We've got the path coefficients, we'll just call this path A and path B, so both of those parameters have to be estimated. We also have the variances of our exogenous variables, so we've got the variance for age, variance for years, and then we also have the covariance between these two. So the total number of parameters that are being estimated in the model is just counted as 1, 2, 3, 4, 5, and then 6. So we have 6 parameters that are being estimated in the model. So if we take the number of parameters being estimated and subtract that from the number of distinct elements in the covariance matrix, we see that the degrees of freedom for the model is 0. And when the degrees of freedom is equal to 0, we have what's called a just identified model. And what that basically means is that we have just enough information within the variance-covariance matrix to uniquely estimate the parameters within the model. So with just identified models, it's also important to note that trying to evaluate the global fit using fit statistics is pretty much pointless, because the fit statistics are going to say that we have a perfect fit of the model, and what's going to happen is that with a just identified model, that will always be the case. So it doesn't really give us really any usable information to try to evaluate the fit statistics. About the best thing that you can do is to just look at the individual parameter estimates and their respective tests. So to kind of show you what I'm talking about, let's try this out with with this model right here. So we have age, years, predicting deference. So there's our model right there, and so in this case, I'll go ahead and save over the previous demo, and I'll click on Calculate Estimates. And so now you'll notice that when we do this, down here it says chi-square is 0, degrees of freedom is 0. If that degrees of freedom is equal to 0, that's indicating that we have a just identified model. So if I click on View Text and look at the model fit, you'll notice that the degrees of freedom is 0, and then it'll look like like the CFI is 1, you've got GFI 1, you've got the RMSEA looks like it's actually that's not for the current model, the default model, but that's the independence model, so that's not really telling us anything either. But basically all of this is kind of signifying that we have good fit, perfect fit of our model to the data. And in fact, if you look at if you were to run this model using Lisserl, it would actually say that the model fits, essentially that it fits perfectly. And again, what that basically translates into is that you've explained all of the variation in the variance covariance matrix with this particular model, so there's nothing left over. And again, that just means that in terms of talking about goodness of fit, overall goodness of fit, it's not particularly useful to discuss that. So, but you still do get the model estimates, and so you could still, even if you have a just identified model, you can still interpret the model estimates in terms of the path coefficients and significance levels. Okay, so also, if you looked at the residual matrices, you'll also see that residual matrices, all of the residual covariances are 0. You can also see the standardized residual covariances, all of those are 0. Again, that's just reflecting that we've used up all of the information that was contained in the variance covariance matrix. So there you go. So now, models that contain degrees of freedom that are greater than 0 are referred to as over-identified, and these are actually, in terms of looking at the overall goodness of fit, these are the ones that we pay attention to when we're looking at the model fit statistics. In fact, Byrne kind of refers to these models as having particular scientific use. I like the description. So here's an example where, kind of going back to the original model, we have basically 5 variables. We have age, years, deference, support, and sentiment. So if we think about it in terms of just counting up the number of elements within the variance covariance matrix, the number of unique elements within that matrix, we would just say 5 variables times 6, and then divide that by 2, and you can see that we have 15 distinct elements within the covariance matrix. The number of parameters that are estimated within this model, we have the variance here, and a variance here for the 3 errors. So that's 3 parameters right there. We have this path right here, this path right here, this path right here. That's 3 more. Then we add this path, and this path. So we have basically 6 path coefficients, 3 error variances. We have 2 variances for the exogenous variables, age and years, and then we have 1 covariance right here. So the degrees of freedom in the model is just computed by taking the 15 distinct elements within the covariance matrix, subtracting the number of parameters estimated, and the degrees of freedom for the model is 3. So, kind of going back then, and I'll just kind of reopen this. Let's see if I can go back. I think this one's it right here. So now when we run the model, you'll see that in AMOS, you can see right here it says degrees of freedom is equal to 3. And clearly, we can click on this and you can see the unstandardized estimates, standardized estimates, and so forth. When we click on this box right here and go to model fit, now you can see again the degrees of freedom for the model is 3. CFI is 1, TLI is actually over 1. Both of these are obviously indicating very good fit of the model. The RMSEA for our default model is 0, also suggesting extremely good fit. If we want to go, let's see, actually if we want to go to, I'm going to re-estimate this, and I'm going to also ask for the residual moments as well. And when we go to matrices right here, you can see now we have elements within the matrix that are non-zero, and that's just indicating that we're not using all of the information in our variance covariance matrix to uniquely estimate the parameters. And so there are potential other respecifications where we might get some of these values closer to 0, but basically the overall model, despite that, is fitting quite well. Okay, so and you can also get your parameter estimates and so forth in addition to the model fit statistics. One final version of model identification that we'll talk about is the underidentified model. And underidentified models are ones where the degrees of freedom are less than 0, or is less than 0. And basically what happens is that there's not enough unique information in the covariance matrix to uniquely estimate the parameters within the model. So here's an example right here where basically we have 4 variables. That would mean that basically in this case we would have 10 distinct elements within the variance covariance matrix, and we're estimating 11 parameters. So in this model right here, the degrees of freedom is -1. And so if you click on notes for the model, you can see right here it says degrees of freedom is -1. The model is basically unidentified, and saying actually in order to achieve identifiability it will be probably necessary to involve or to impose 1 additional constraint. And what that means is, for example, we might fix, say, this covariance right here. We might fix it to 0, in which case that's just basically achieved by removing this covariance right here, and then we would have a just identified model. So that pretty well ends this discussion on model identification. As I said before, this topic can be fairly complex, but these are 2 of the main issues are two substantial issues that you need to pay attention to when you are specifying your SEM models. Obviously, I've just talked about this in the context of regression and path analysis. If you want a more extensive discussion on these issues, you can refer to Klein in his book from 2016. It's Principles and Practice of Structural Equation Modeling.